Hi, everyone. My name is Pedro Ojeda, and I'm working at the High Performance Computing Center North in Sweden. And today we have with us Kristoffer Carlsson, who is working at Julia Computing. So Kristoffer will talk about some topics that are relevant for HPC, high performance computing. For instance, SIMD, which is quite useful for linear algebra operations, for instance. Yeah. And as you received the information in the emails that you got from my colleague Birgitte, this talk will be recorded. And if you don't want to be recorded, please turn off your camera and also your microphone. So I leave you the floor, Kristoffer.
Thank you, Pedro. I will share my screen and start the slideshow, and then you can see if you guys can see my screen. Can hear me okay?
Yes.
Okay, great. So let's get started. So thank you, Pedro, for the introduction. I'm Kristoffer Carlsson. I work at Julia Computing, and today I'll talk a little bit about Julia in the context of high-performance computing. I put the slide link here. I will also show it in the end, so you don't have to copy it now. But yeah, so let's get going. So first, just a short outline of what I will talk about today. So this talk is not really like a Julia intro talk, but I thought I would give a short introduction to Julia anyway, just for people that are maybe don't know so much about it. And then I'll talk a little bit about performance with modern hardware, not really Julia specific, but more in general. And then we'll focus a bit more on Julia again with Julia's compilation pipeline and a bit about the different Julia features that relates to performance. And then in the end, I'll do some kind of summary. So first, let's talk about the Julia language then. It was created at MIT, and the first public release was in 2013. And then 1.0 was released in 2018, and with 1.0, there's no more breaking changes. So code you write now will keep working in the future for future Julia releases. And the latest release right now is 1.7.3. And it's quite young in sort of, if you measure it in programming language years. I put some other dates here. Fortran 77 was released in 1978. Python 1.0 was released in 94, and then R 1.0 was released in 95, and then Julia was in 2018. So it's still quite a new language. But it's a general purpose programming language, and it has some features that make it sort of especially suitable for scientific computing and high performance computing. And I'll try to show some of that today. It's supported by NumFocus since 2014, and NumFocus is sort of a non-profit organization that support open source projects. It's JIT compiled and just-in-time compiled, so it compiles things just before you run a function. So it's not like C where you compile something beforehand, but you sort of compile things as you run them. It's MIT licensed, so a quite open license. You can sort of use it for whatever you want, and it's free and open source and so on. It's garbage collected, so you don't have to manually free your memory. It happens automatically. And the aim is to solve what's called the two-language problem, which is defined as when you prototype something in a productive but slower language. Let's say you write your prototype in Python, and then you write your sort of final version in a fast language, maybe C++. So you sort of do the implementation twice. There, one to sort of in a productive way, but it's slow, and then one when you do it another time in the fast language. So Julia tries to be sort of like you should only have to write your code once, and it should be sort of fast enough. So just to give like a very high level overview, Julia sort of has some kind of batteries included. So if we look at data structures, it has some sort of a Python feel. So we can create an array here, similar like how you would do it in Python. And here I have an integer in it, a string, and a tuple. And then we can call methods on this array, like we can reverse it or something. We can create a dictionary or a mapping between some keys and values, and then we can index into it to retrieve the value for a given key. Or we can have some methods here where we try get the key, but if it doesn't exist, we get some default value. Can do sort of comprehensions here, where we write it like this, like you would do in Python, with a filter there in the end. So that's sort of a little bit similar to Python when it comes to data structures. But then it also has this linear algebra part, which has, so it has like linear algebra solvers, SVDs, sparse matrices, and so on. So we can, for example, create a random matrix here, 3 by 3, and a random vector. We can do a matrix multiply, matrix vector multiply, or a solve here with backslash, similar to MATLAB. We can compute the SVD of this matrix, or we can create sparse matrices and do sparse solve. So when it comes to linear algebra, it's a little bit similar to MATLAB, I would say, both in the syntax and the functionality. So let's look a little bit about aggregates or structs and polymorphism. So you can create a struct here, which I call a circle, which has some sort of radius. And we have a method here that acts on a circle and computes the area. Then I have a second struct, a rectangle with the width and height. Then I have another method which acts on rectangles and computes the area in another way. And I can create a vector of these shapes. And then I can call a function on the shapes. And it's going to either pick this area function or this area function, depending on the type of the argument then. So the first one is a rectangle, so it's going to call this method because the first one is rectangle, and so on. So this is sort of polymorphism in Julia. And a little bit similar to polymorphism, let's say I define a function here, I just do x squared plus x, and I can call it with an integer, of course, I get a value. I can call it with a float, I get a value. I can call it with a complex number, does the same thing. Here I call it with a matrix, and you can square a matrix and add it, so it works out for that too. And then here I'm loading a package called forward diff, which does automatic differentiation, and I call that with sort of a dual number. And even though when I wrote this function, I didn't know anything about this package, sort of, you can still call the f function here because the dual numbers implement these methods. And one sort of key thing with Julia is that it specializes on the arguments. So there's what's called a macro in Julia. You can write at code native, and you're going to see the assembly code that's generated for a certain function call. So if I look at the generated assembly code for f here, when I call it with an integer, so you have an integer multiplication instruction here and an integer addition. But if I call it with a float, I have a float multiplication and a float addition. If I call it with a complex number here, I have a complex number with an integer real part and an integer imaginary part. I have some integer instructions here, and with the dual, I get some other instructions. So even though if I go back, I only wrote f once, depending on the input types, a new sort of version of the function is instantiated with specified optimized code for that specific argument type. So that's sort of very short, quick summary of Julia, how it works. So now I want to sort of preface my discussion about the performance things in Julia by talking a little bit about sort of modern hardware and performance. So if we start off thinking that there's no threads, there's no multi-processing things, and just look at the standard single core systems, and we have a program that we're running, there's assembly instructions, and that the CPU is executing. CPU has different layers of cache, but it also needs to talk to memory. And of course, we also have storage, which we load into memory and store things. This is sort of a very, very high level overview of what the computer does. And what sort of makes code fast then? Well, the first and most important thing is, of course, good algorithms. But these are not really language specific. And this talk here focuses a bit about languages. So I'm not going to talk about algorithms at all. But those are, of course, the sort of the most important thing. In most cases, you can't make up a bad algorithm by writing fast code. You need good algorithms, firstly. Then if we look at actual hardware here, we can look at memory accesses. So we want to have temporal locality or keep things in cache. We want to have spatial locality. So we don't want to pick memory from all over the place. When we pick memory, we want to have it in a constrained space. So we sort of reduce the number of cache line we fetch. We try to avoid read from RAM, which is slow. We try to avoid especially reading from storage because that takes forever. Other good things is to reduce the number of unpredicted branches. Modern CPUs, they have very deep pipelines. They do a lot of speculative executions. And if it predicts a branch wrong, it has to sort of go back. So that takes quite a long time. Also, want to reduce the number of indirect calls or indirect jumps. It's also about the computer being able to predict what's going to happen. And of course, the instructions we run, we want them to be sort of optimized and the best for the architecture we're running it on. So for example, if there's specific SIMD instruction, we want to be able to run those. If it has fused multiply add, we want to run those instead of doing separate multiplies and adds and so on. If you want to make this sort of a summary, if code that's generated is unpredictable, like the processor don't know what's going to go on, like in this traffic situation here, you don't know what's going to happen, who's going to merge, and it's going to go on, so it has to go really slow. But if things are kind of predictable and you know what's going to execute in the future, code can be sort of faster. But then, of course, we're not living in a single core, single thread world. So we have the first step is sort of shared memory parallelism. So we have multiple instruction streams that the CPU is executing concurrently. And then we, of course, have multiple stores and reads from memory. And that brings in other challenges. So, for example, we have cache coherency, that the different threads need to see the same memory, even if one thread is mutating memory. So we can get this thing called fault sharing. When we have multiple threads writing and reading from memory, we have higher pressure on the memory bandwidth, which is finite bandwidth. We might have critical regions that we need to only execute on one thread at a time. So we might have bottlenecks from locks there. We might have some scheduler that schedules different threads to run, and that might have some overhead. And then we want to do some load balancing so that we're not executing most stuff on one thread, but there's sort of a evenly spread execution of work. And then going one step further, we also have distributed memory parallelism, where we have multiple what I call nodes here, where in each node we have a multi-threaded system, but then we have many nodes and the nodes talk to each other. And then, of course, we want to minimize the communication between nodes, tend to be quite slow. And if we have a big system, we have some sort of topology where the nodes are connected to each other in different ways. And it's not equally fast for one node to talk to every other node. So that also has to be taken into account. There's sort of many layers of things to take into account here when we want to write performant code. And what's getting more and more popular is these accelerators, which is like custom hardware made for certain purposes. So what's been used quite a lot is TPUs. It's originally used to do graphics on the screen, but they're now quite common to do certain operations that are heavily parallelized. So this is popular in machine learning. And then, for example, Google have these TPUs, which is sort of a hardcore version of GPUs, which is made to do certain small matrix multiplications really quickly, which is useful in machine learning. And these custom chips, I would say, are getting more and more common for specific workloads. So I think machine learning has driven this quite a lot. So if we look at a language, then what does a language need to provide to be able to give good performance? Well, one thing is control of memory layout. We need to have, if we have an array of things, it needs to be packed tight. Even if we have user-defined aggregates or user-defined structs, we can't have an array with only pointers in them, and then we have to chase the pointer and so on. So we need to be able to control the memory layout. We need to have an optimizing compiler that sort of targets the architecture that the code will end up running on. So as I said before, we need to run the best instructions for this given processor. We can't just compile some generic version. It needs to be for this specific CPU. Typically, we either need to do some kind of static types, like in C or something, or we need to run type inference. And I will talk a bit about what type inference is later. But when we call methods, they are often based on the type of arguments. And if we don't know in advance the type of arguments, we have to do a virtual function call, which is an indirection, which will be slow. And there's also many other optimizations that require us to be able to do devirtualization. So for example, if we want to inline a function, we need to know what the actual function is going to be called. It's good to have first-class support for multi-threading, but also first-class support for multiprocess gradations. And it would be nice to be able to sort of drop down to a lower level when needed. So if the compiler by itself does not do such a good job, sometimes it's nice to be able to write like explicit SIMD stuff and so on. And I'll try to show that Julia, at least in my point of view, ticks quite a lot of these boxes, and it's a quite good language if you want to write code that has good performance. So to start with Julia, then I will talk a little bit about the compilation pipeline. So what I mean with that is that when what we will write Julia code, it's source code, it's text, it's like this. And it then goes through a pipeline here, certain steps that in the end gives us assembly instruction that the CPU is executing. So I will sort of walk you through the whole chain here of going from source code to assembly code. So the first thing that happened is parsing. So we just have a string here with Julia code. And then in Julia, we can call meta.parse in a string. And then I'm just going to sort of show what's inside there. And then we get an expr expression or an expr struct. And that is just a parsed version of this source code. So we have a certain expression with a function head here because this is a function definition. And then we have a call with a mySum and an x here. So it's just normal parsing. That's the first step. Then something happens called lowering. And lowering is transforming code to a less complex form from the point of view of compiler. So some example of that might be if you have an array comprehension, you could write that as a loop, which is sort of a simpler thing. An array comprehension is a higher abstraction. Then a loop could be written as a set of go-tos, which is also a lower complex form. So in Julia, you can call code lowered on a function here, and it's going to call the lowered things. The lowered code is going to be shown. So here we can see the s equals 0 is still there because it's very simple, but this for loop has been transformed into the Julia has an iteration protocol and has transformed the for loop into that. And you can see we have go-tos here, which goes to basic blocks and so on. So this is much simpler for the compiler to reason about than these things, because this is sort of a more basic version of the language. And when we have the lowered form, the next step is to run type inference. And what type inference is to assign a type to every statement in the code. So here I can do code type, and I call the function here, and here I have a vector of integers. So Julia figures out here that x, which is the input argument, is a vector of integers. That's sort of the base case. But then it goes through the rest and figures out what will be the type of all the rest of the statements. So it figures out here that here's a check for a variable towards something else, and triple equal check, and that will be a bool. But before, when we had the lowered stuff, we didn't know what type things have. So here, after we have run type inference, we know the types of all the different statements. We can also see this is the return value of the function. So Julia has figured out that this function will return int64 when we pass in this value. And I want to spend a little bit more on type inference because I would say this is the most important step in the sort of compiler pipeline. Because as I said before, the types of object determines what methods get called. And the type inference here enables almost all other optimization that's going to happen afterwards. So for example, devirtualizations and inlining, if we didn't know the type of things, we couldn't do this. And if we don't have types, it's hard to say much at all what the piece of code is doing, because the types determine what methods are going to get called. But Julia is a dynamic language, and it's not always possible to determine types. So as an example here, I can create a vector of an any type, and that's a vector that can hold an object of any type. So if I look at the type of x here, it's a vector of any. So I can use this code warn type macro, and I'm going to call the first of x, which picks out the first element of x. And what you can see here then is that this call to get index, which is taking out the first element, has been type inferred to any, and it's red here, because it could be based on the types. It's impossible for Julia to know what the actual type will be returned, because you can put anything in this type of vector. So here, Julia will emit a virtual call or a dynamic dispatch where this fails. So it's sort of a compromise. But then when we actually at runtime look at what type this object has, we'll do another inference after we've called that. So I write here that we reinfer after dynamic method lookup, but before the method is executing. So we sort of try to infer as much as possible out to the places where we can't anymore. And then those places, there has to be a dynamic dispatch based on the runtime type. But try to do this as little as possible. And that's why this tool is here, the code warn type to see, and it's marked in red here, because this is generally, if you want performant code, this is generally to be avoided. And then after type inference, we're going to use LLVM, which is a compiler backend, which is used by many languages. So C, C++, there's a compiler called Clang, which uses it. Rust and Swift also uses this as the compiler backend. And LLVM does a large number of optimizations. So it can, I just wrote some example here, loop unrolling or vectorization, SIMD. So here, if I call code LLVM on this function here, and I print some of it here, you can see here that it generated some add instructions. And here you see some SIMD because it's using these vector width of 4 here, and that's unroll the loop and so on. So here a lot of optimizations have happened. And then finally, LLVM will also pick out the assembly instructions to run. So here we can see that if I wrote code native, it shows the assembly code. And here we also have some SIMD instructions here that it picked for us. So this was all, if I go back far, this was all from this function and the input type of a vector of integer. And then the whole pipeline generated this stuff as assembly code. So I want to show some Julia features which relates to performance then. So one thing that I talked about earlier was the tight packing of data in vectors. So if I have a vector of integers here, if I check at the type of this V here, it's a vector of integers. And this integer has 8 bytes, it takes 8 bytes. So we would want this vector to take up these 8 bytes, the size of each element, multiply with the length. And it also does that because the data is just stored in line for integers. And also if I create my custom struct here with an integer and some floats in it, this struct is a bit bigger, it's 16 bytes. And if I create the V2 here, a vector of this struct, it also has the same number of storage as you would expect if things are stored in line. So just because you write your own struct doesn't mean you get any sort of worse performance compared to using an integer, for example. SIMD is another thing in Julia. So it can happen automatically from the LLVM auto-vectorizer. So if I take 2 tuples here and I create a function that just does an element-wise add, and I look at the code native, you can see we get this VP add, which is a vectorized packed add instruction here using the SIMD register. So this is AVX2 instructions. But there's also a package called simd.jl, and you can write explicit sim. I'm not going to go through this code, but you can if you want to. For example, this is just a vector addition that's been unrolled and so on, and it loads data into vector types and it adds them and stores them back and so on. So if you want to, you can use this explicit SIMD. And an important thing is that this SIMD code is compiled against the target architecture. So if I check the code native of plus, when I have 2 8 wide vectors here, you can see I get 2 vector instructions, 2 adds here, because the width of the SIMD lanes on this hardware can only fit 4 of these float 64s in it. But if I run it on another machine, an AVX512 machine, and I run code native, you can see it only generates 1 add instructions, because on this machine it can fit all 8 floats in 1 lane, so you just need to do 1 addition. So the code gets compiled, depending on where you run, it gets optimized. We also have threading in Julia, so you can start Julia with a certain number of threads. And one way of using that is using a threads macro, and you just slap that on a for loop like this. So in this loop, I just compute the exponential on a bunch of numbers, and I just do threads here on the loop. And I can use this package called benchmark tools to time it. And depending on how many threads I do, I get different scaling here. The scaling is not perfect here. It might be memory bound or something, but you can see at least 5.5x increase. We're going from 1 thread to 8 threads here. You can also do a bit more. You don't only have to put it on loops. You can spawn certain tasks on threads. So if I have a loop here, I can spawn a task that's going to be run on its own thread. And then I have a sync macro here to sort of do the synchronization when all of them are done. And here different, I put the thread ID in the array, and then you can see different threads from different tasks. When it comes to distributed computing, there's a standard library called distributed, and you can just add processes here. And then there's some built-in stuff. Let's say you want to do a reduction, you can do the at distributed, and the plus here means you're going to do some reductions. And then, for example, you can do a loop that just computes the integer of a random bool, so either false or true, and sum them up, and you get approximately half here. But then Julia will split up this this range and distribute it on workers. But if you need more control, you can sort of here you can define a function using the everywhere macro, and then you define it on all the workers, and you can spawn tasks on, let's say I want to spawn it on any worker, and then it's going to run this and I get back a future. Can spawn another one and another worker, and then I can fetch these, so on. So this is a bit more control here. You can spawn tasks on different processes and so on. You can also use MPI, which is common on sort of high performance computing clusters. So for example, here I'm just doing the hello world in MPI. So I load the MPI package, I initialize it, set my communication here, and then I print something, and then I have a barrier, so wait until everyone is done. And then I can use the MPI exec here to run this code, and it's going to use the MPI to pass messages. There's also a package called cluster managers, which is quite useful if you're running Julia on sort of high performance computing clusters. So it has support for many different job queue systems. So here I just took the example for using Slurm here. So you just load the package, and then you can see here there's different arguments you can pass to the Slurm command and so on. So it's a bit sort of easier than just using bash to start your queue. Then when it comes to accelerators, so for example, for NVIDIA GPUs, there's CUDA.jl, and that is a Julia to CUDA compiler, and it also has support for calling this into QBLAS, QDNN, QSparse, QFFT, which are libraries written by NVIDIA. There's also support for AMD GPUs, and also a bit more experimental stuff, like Intel has this one API, and there's quite a lot of activity there in this organization. So just to show you some CUDA.jl usage, so you can just load the CUDA package. And then if you want to do things a bit low level, you can write the CUDA kernel in Julia like this. So this is the classical, vector add between 3 vectors. And based on, your block ID and your block dimension and thread ID, you calculate an index, and then you do the operations. And then you can define here I'm just going to call this, so I define 2 matrices with certain dimension. I define these Q array, which are arrays living on the GPU. And then I call the kernel, and I give how many threads I want to run on, and then the kernel here with arguments. And then I just check that the A plus B here is the same as I got from running the CUDA kernel, and it's what's here. But this is quite low level, and I would say I'm going to show an example of how I think it's more common to do GPU program in Julia. So first, I just want to have some normal Julia code. It doesn't have to be run on the GPU or anything, but I'm going to load a package called tensors, which you can have pretty high performant sort of small vectors and so on. I'll define a planet with some mass and some velocity, and the velocity here is a 2D velocity with doubles. I define how you compute the kinetic energy of a planet. And then the total energy of a vector planet then is if you sum the energy over each planet. Then I can create 3 planets here, and I can look at the size of the planets, this array, and it turns out that it's 72 bytes because each planet has 8 bytes for the mass and 16 bytes for the velocity, and then we have 3 of them, which gives 72. And then I can compute the total energy of the planets, and it turns out to be this number. So this is just CPU code. And I can load my benchmark tools package, and I can time it. Turned out to be 39 nanoseconds for this. Now, let's say I want to run all of this on the GPU instead. So what I can do is I can load the CUDA package. I transform this array to live on the GPU. And then I just call the same function as I did on the CPU, but there's a different input argument. So what happens here is that CUDA.jl will compile GPU code from Julia code. So I didn't need to write any CUDA.jl specific kernels. So instead we have Julia being compiled towards the GPU. And I just want to show a little bit how far you can push this. So I'm going to load another package called unitful, which has units, support for physical units. So now I define my planet to have sort of, it has an M, which is a type of mass, and a V, which is a type of velocity. And now when I create my planets here, I say that the planet's mass is in kilograms and the velocities here in kilometers per second. So if we go back here, you couldn't really know what unit things have here, and you don't really know what unit this value has. So now we have units and everything here, and we can see that even with units, the size of the planets is the same. So we didn't pay anything in memory to add these units. And if I compute the total energy here, we get the same value as before, but now we have units instead. And I can convert this to gigajoule, and now I have a number with units. And I can also benchmark this, and I get 40 nanoseconds now. Before it was 39, so there's no cost in performance here. And I can still just convert this to the GPU and calculate the total energy on the GPU. So even though I have two different packages here and they're working together, I can run it on the GPU. So I think this is pretty impressive composability, how you can take things from different packages and sort of put them together into one thing and still run it on the GPU, for example. So to do a little bit of summary then, modern hardware can only be fully utilized by languages that provide certain features. So you need to be able to control memory. You need to have an optimizing compiler that targets the architecture the code will run on. You want to be able to run multiple threads and multiple processes in your computations. And you also want to be able to target these accelerators or this custom hardware. And I would say Julia is a little bit unique in the sense that it allows these things, but it also still feels quite high level. It feels a little bit like writing Python, for example, but while it still has sort of control over memory and so on, and you can drop down to explicit Sims and so on. So yeah, thank you. That's it for me. I put the slide link again here, and I guess if there's any questions, I can answer them.
Yes, a question, Kristoffer. It is the LLVM that decides the type of vector instructions that will be used, right?
Yes, you can like explicitly also say what intrinsics it should use, like the actual instruction. But if you do things like, let's see where I have it. If you just do things like this, where you just say that I have a vector of 8 floats and a vector of 8 floats, then LLVM will like, oh, okay, I can put that into 2 adds based on, and LLVM will do that decision based on the CPU target. But you can also go even lower level and say that, no, this is the exact assembly instructions I want to run. But then if you run that on a system that doesn't have that instruction, it's probably going to crash or say that it's going to error saying that that instruction doesn't exist on the target. Okay, and someone wants to post the link, that I should post a link in the chat, so I'm going to do that. That's a good idea. So there's the link. So now you don't have to write it down manually or take a screenshot or something. I put it in the chat. And I see people found it because people are coming in here.
Hi, Kristoffer. Can I ask a question?
Yeah, sure. Go ahead.
So I've been trying to use a lot of parallelization and distributed computation on the UPMAX HPC cluster, and
Okay.
I wonder if you have like a recommended reading, like how to structure a program. Like I've been running some minimum working examples on that cluster, and some things don't work as described online. And I think it has like specific to the setup of the cluster.
You mean specifically for Julia then, or?
Yes, yeah. So yeah, for Julia and for different kinds of clusters, and like how to maybe figure out what is the best approach for yeah, for example, Upmax.
So I guess it depends a little bit what errors you encountered, what to do.
I just thought some general, like general reading, if you would have anything on top of your mind.
Yeah, I guess the cluster managers package, it has some examples and documentation how to submit jobs.
Yeah.
But then I think there are some JuliaCon workshops and so on about distributed computing, but I'm not sure. I don't have anything on the top of my head explicitly for this, so maybe you just have to try Google a bit and see.
Yeah, I'll continue Google. Yeah, we'll do
Yeah.
that. Yeah, okay. Thanks so much.
Well, I think I can add something here regarding HPC. In particular, if you want to port your code to an HPC center, then it's highly recommended to start with a profiler. So Julia has several tools to profile your code and see where are the bottlenecks, right? And also there is some integration with the other tools like Intel VTune that allow you to monitor in detail your code.
Yeah, VTune is pretty great, I would say. So I think it's supported. I'm not sure if you have to recompile Julia to enable the support for it, or if it's actually enabled by default now. But yeah, there is support for Intel VTune, for example.
Can you spell that out so I can Intel V2?
Yeah, it's
in the chat or something. Yeah. Okay, V2. Okay.
It's this. So it's basically a profiling tool, and you run your code with it, and you can sort of see different threads and what's going on.
Ah, perfect. Yeah, it's like what they have in MATLAB.
Yeah.
Okay. There's some. Yeah. Okay, someone wrote in the chat about Julia on Bookmarks also. Okay, thanks for the input.
Yeah, this is a good thing about the HPC channel in the Julia Slack. So I would say the Julia community is very, very open and they're eager to help. So instead of just Googling and trying to find blogs and articles, actually like writing a question on either there's a Julia discourse or on the Slack might be also a good way to get help a bit more quickly. So that's a good thing.
And I can Google how to get on that.
Yeah, there's
on the slide.
I'm pretty sure there's if you go to the Julia here and just Google Julia Slack, there's you can just join us. I think you need to accept the code of conduct, and then you get a link to go in.
Okay. Thank you very much. I really appreciate it.
Yeah, no problem.
I can ask a question. It's more practical than what has been asked before, but it's along the same lines. I find that Julia is a fantastic program, and you can run it quite nicely on your computer. You can use all the packages you want in your computer. As soon as you go to Slurm, nothing runs, I find. Is there a set of very clear instructions about how to do that? Because I've tried really to Google this, and you get a lot of stuff, but most of it is outdated by a few years. So it's really very difficult to find something reliable.
Yeah, that's annoying. Maybe I would give the same recommendation there. If you, for your particular error, if you just write that in the Julia Slack HPC channel, I'm sure people will help you out. The problem with many new things is that Julia has been moving quite quickly, and people have written articles about it a couple of years ago, and they might be outdated by now. So hopefully with Julia 1.0 being released, that should be less and less of a problem, but it's still close enough to that point that there's still old stuff being written. So, yeah.
Yeah, and also I can add that the different SNCC centers have a support email, and if you have any issues with the software that is installed and you want to communicate with us, you can write us an email, and it would be great if you provide us with a test case, yes, that reproduces the error, right? And in that way, we can take a look and give you more feedback, yes, a useful feedback, and that would be great.
Thank you.
So I could ask a question. Can you guys hear me?
Yeah.
Yeah. So in Sweden or through SNCC, are there any groups that run large-scale HPC using it, Julia as their main programming language? Like, can you find some information on the web somewhere?
Not sure about Sweden. Like the biggest I know that runs it now is they're run from Caltech. They have these big climate simulations, which are quite big, but I don't know so much about in Sweden. I know a bunch of like PhDs that run their own projects on clusters, but I don't know if you would call that large scale. I'm not sure. Like I don't personally know about any like really big scale computations that are being run. But I'm not super involved in sort of the HPC community, so I might miss things.
Sure. What's the Caltech project thing again? Maybe I can take a look at it.
I think it's Klima. It's Klima. It's
Maybe someone's posted a link.
thing. Yeah, someone posted a link to.
Yeah. Okay. Thank you.
Is there any further questions to Kristoffer?
If you guys have any later questions to me, you can find me on the Julia Slack or my email here, and feel free to ask me anything about Julia. So, yeah.
Okay, so we can then thank Kristoffer again.
Yeah, thank you. It was fun to
Yes.
be here. I'm happy that so many people showed up.
Yeah.
Yeah, thank you.
Yes, and see you.